We're going to look at something called the second derivative test here in a moment. And what this boils down to is how the second derivative is related to relative maximums or minimums. So as you can see here, the second derivative and relative maximums and minimums. Okay, once again, second derivative can help us find relative maximums or minimums, and is based on a couple of observations here that I want us to make. You see the graph, and what I want you to recognize is that a value C right here, that's an X value. If we look at the point on the graph there, then if we look at that tangent line is horizontal. So C, in this case, is a place where the first derivative is 0. Okay? C is a place where the first derivative is 0. So C is a critical number of the first derivative, isn't it? And we also see that the graph is concave down there. Okay? So the observation is that if our graph is concave down, and we have a critical number of the first derivative, that is, we have a horizontal tangent line, then we know that at C we have to have a relative, what did I say, a relative minimum? Ooh, my bad. A relative maximum. So if we're concave down and we have a critical number, then we have to have a relative maximum, and it's based on the observation of this graph. Let's make another observation. Well, the second observation has to do with the second graph. Obviously very similar. And the observation is that if our graph is concave up and we have a critical number where the first derivative is 0, that means we have a horizontal tangent line. So if the graph is concave up and we have this horizontal tangent line, then the graph has to have a relative minimum. So concave up is telling us we have a relative minimum, concave down is telling us we have a relative maximum. But of course, this has to do with critical numbers where the derivative is not undefined, but where we have a horizontal tangent line. So the critical numbers are where the derivative is 0. Now, let's make another couple of observations. Concave down means that at that particular critical number, the second derivative is what? If it's concave down, the second derivative is negative. And in this case, to be concave up, the second derivative at that C value has to be positive. And so that's really the observation, is that if the second derivative is negative, that tells us we're concave down. And if it's negative at a particular critical number of the first derivative where we might have a maximum or a minimum, we know that it's actually a minimum because we're concave down, we have to have a maximum. If the second derivative is negative, then we have a maximum. If the second derivative is positive, it means we're concave up. So it has to be pointing up, so it has a low point. It has a minimum. Second derivative positive means we have a minimum. Now this is only true when our critical numbers are critical numbers of the first derivative. Remember, that's the only place we can have maximums and minimums. Now this is basically a summary of what's called the second derivative test. Now I'm going to write the second derivative test down next, and we'll pause as I do that, and we'll come back and look at it in whole. But here's the statement of the the second derivative test. Okay, so that's what we're discussing here. Remember, we have a first derivative test. That's why we use the first derivative to find the relative maximums or minimums. And this is saying we can also use the second derivative test in some cases. So this is a summary of what we have above. Let f be a function and C a critical number of the first derivative for which f prime of C is 0. So it's not where the first derivative is undefined, but where it's derivative. Okay. If f double prime of C, so now we're taking that first derivative critical number and we're checking it in the second derivative. Number 1, if the second derivative is positive then then we know at that critical number, the function f has a relative minimum. And the way that's backwards. Second derivative positive, we have a minimum. That seems backwards. But here's what we need to remember. Think of second derivative positive means concave up. And so if we're concave up, we have to have a minimum, don't we? On the other hand, if the second derivative is negative, then we have a maximum at that value, a maximum. Remember, c is a critical number of the first derivative, okay? And this seems backwards also. If the second derivative is negative, we have a maximum. But it's not really. We need to think. Second derivative negative, that means concave down. And if we're concave down, we have to have a maximum, don't we? So we need to think in terms of concavity here, and then that will help us remember rather than just think backwards. Now, we've just discussed here if the second derivative is positive or if it's negative. What if the second derivative is actually 0 at that critical number? Well, then we say the test fails. See, if the second derivative is 0, the test fails, which really means the test is of no use. The second derivative test doesn't tell us whether we have a relative maximum or a minimum, or in fact, neither. I mean, it doesn't tell us anything. And so we still don't know whether we have a maximum or a minimum, or we have neither a maximum or a minimum at the critical point C. So in this particular case, if that happens, then we have to use the first derivative test to find out whether we have a relative maximum or whether we have a minimum or whether we don't have either one of those. So we have to be aware of that we may not always be able to use the second derivative test. Don't forget, for the second derivative test, you use the first derivative critical numbers. But you test those first derivative critical numbers, you test them in the second derivative. You've got to keep that in mind. Why? Well, after all, the first derivative critical numbers are the only places that you can have relative extrema. So that's the places that we're looking for relative extrema. So that's the reason we use those critical numbers, but we test the concavity at those critical numbers. That's the reason. Keep that in mind. Let's now look at an application of this, how we actually put it to use when we have a real problem. Okay, here's how we use the second derivative test to find relative maximums and minimums. Remember, first we need critical numbers. We need critical numbers of the first derivative. And I'm going to pause right here and just stop and think what we've already been doing. We first started out finding relative maximums or minimums. And to do that, we found the critical numbers of the first derivative because that's where we could have them. And then we used the first derivative test. That we went to see whether the first derivative changed signs at those critical numbers, because that meant we changed from increasing to decreasing or vice versa, which would mean a relative maximum or a relative minimum appropriately. And then after we studied that, we started talking about concavity. Now, when we're studying concavity, we looked for the critical numbers of the second derivative, and we looked for changes of sign in the second derivative because second derivative indicated concavity. Okay, but here, of course, now, what we're going to do is we're using the first derivative to find out where we might have maximums and minimums, but then we use the second derivative to find out which it is. So we're not interested in the second derivative critical numbers because those tell us about inflection points. First derivative critical numbers tell us about relative maximums and minimums. So to find those first derivative critical numbers, we need to find the first derivative. And so in this function, the first derivative is 3x squared minus 6x minus 24. And so we need to know where this is equal to 0. And so, of course, we simply set it to 0 and solve. Now, I'm noticing that that we could factor out a common factor of 3, and we'd have 3 times x squared minus 2x minus 8 equals 0. And then probably I would even go further, and I would divide both sides by 3. Come up here now to save some space. And that would just really leave me, my 3's would cancel, wouldn't they? And I'd have x squared minus 2x minus 8 is equal to 0. That would really be an easier equation to solve. And we try to solve this by factoring, and I think we can factor this as x minus 4 times x plus 2 equals 0. And so when we get to that point, then we can see right away that x equal 4 and x equal negative 2 are the solutions. And so those are the critical numbers, and that's the important part here. Oops, those are the critical numbers of f prime. And so those are where we need to know whether we have maximums and minimums. Now, the next thing we do is we test these critical numbers in the second derivative. Okay, but to do that, we need to know the second derivative. So now we calculate the second derivative. And we look above at the first derivative to calculate, and we see that we'll get a 6x minus 6. So now the second derivative test says we take those critical numbers of the first derivative. Second derivative test, that's what we're dealing with now. So we take the critical number, let's say 4, and we put it in, now that's from the first derivative critical number, isn't it? But we put it into the second derivative. And we calculate. And in this case, we get 24 minus 6, which of course is 18. Now, remember the second derivative test says if the second derivative is greater than 0. Well, what does that mean? See, what does that mean? The second derivative is greater than 0 out here at where 4 is, which means the graph is concave up if it's greater than 0. So that tells us that we have a minimum. So there is a relative minimum, okay, a relative minimum at x equal 4. Now, of course, that doesn't tell us what the minimum is. The minimum is a y value that we get when we put 4 into the original function. See, this is kind of an issue. We've got the first derivative, we've got the second derivative, we've got the original function, we've got these critical numbers. Where do they come from? What do we put the critical numbers into when we're trying to decide? And then how do we find the y? And I know it's just, oh, there's so much to remember. Well, the second derivative is to tell us whether we have a maximum or a minimum. But when we're talking about a maximum or a minimum, we're discussing the original function. And so we need to put this f of 4 into the original function. I mean, this 4 into the original function now to find a y value. And so we would end up with x cubed, or 4 cubed, minus 3 times x squared, or 4 squared, minus 24 times x, which is 4, and then plus 32. And when we do that, we get a y value of negative 48. And so negative 48 is the relative minimum. It happens when x is 4. Okay, now, we've only tested one of the two critical numbers. We need to test the other critical number. And so we take the other critical number, which is negative 2, and we put it into the second derivative. That's the second derivative test. And so it's 6 times, remember the second derivative is 6x minus 6, so it's 6 times negative 2 minus a 6. So that ends up being negative 18. Now, Of course, we get a negative 18, that's less than 0. And so the second derivative is negative. Well, when the second derivative is negative, that was positive up here. When the second derivative is negative, then we have a maximum. And the reason we have a maximum is when the second derivative is negative, we actually are concave down. And if we're concave down, then we have to have a maximum. So that tells us that we have a relative maximum at the x value of 2. At the x value of negative 2. That tells us the x value. But the relative maximum is a y value. It is a y value that we calculate by putting negative 2 into the original function. And so when we do that, we'll have a negative 2 cubed minus 3 times a negative 2 squared minus 24 times a negative 2 plus 32. And when we go through all that calculation, we get 60. And so this happens to be the relative maximum. And we know it's a maximum not because it's bigger than the other value. It's a maximum because we're concave down. Remember, we can't tell about maximums or minimums by comparing numbers. But in this case, we know that it's a relative maximum because we're concave down there. Well, let's look at this graph now and see how proud we're. This is actually an easier test than the first derivative test. Let's look at this function f of x equal x to the fourth.
Well, I'm sorry for all the flipping and going on here. Let's get back to what we were doing. I apologize for that. What we just found out is by using the second derivative test, we found out at negative 2 we had a relative maximum, and that relative maximum was 60, so that corresponds to here. And at positive 4 we had a relative minimum, and that relative minimum is associated with this point, which keeps popping up, but you can see that y value is down there about negative 48. So that's what the second derivative test did for us here. And it's a great use, an easy tool, sometimes a lot easier than using the first derivative test. Well, let's continue now with the last idea.
And find its derivative, and of course its derivative is 4x cubed. And so if we look for the critical numbers, that would be simply x equals 0, because that's where that is a derivative, equal to 0, isn't it? Now if we look at the second derivative, that would be 12x squared. Actually, I want to do a couple of things here. If we were now to test the critical number of the first derivative in this second derivative, that is, if we were testing f double prime at 0, we would just get 0, wouldn't we? And so here's an example where we can't tell whether this is going to have a maximum or a minimum, or neither one at all, because the second derivative test fails here. And that's really what second derivative test fails. Let's look at the graph right next to it here. I'm going to put the graph up here, but that's really the big issue. The second derivative test fails. So I've gotten a little bit ahead of myself here. The first thing I wanted you to know is that the second derivative test fails, and that we would have to use the first derivative test if we didn't have a graph to decide whether we have a relative maximum or a relative minimum. And remember, the reason the second derivative test fails is because at the critical number of the first derivative, which is 0, f double prime of that number is 0. So that doesn't tell us. We don't know about whether this is concave up or concave down at all. We don't know that at this point. Now, so Ignore what I've written right here for just a moment. Let's come down here and now say, oh, we'd have to use the first derivative test to find out. See, the first derivative test, we're still interested in finding out about maximums and minimums, and we already obviously see that this has a relative minimum, but we'd have to use the first derivative test to find relative maximums or minimums if the second derivative test fails on us. And so what that would mean, remember, is that we would look at the value x equals 0, and we would look at the interval that value creates to the left and the interval that value creates to the right. And then we would be testing the first derivative. Okay, testing the first derivative in those two intervals. And so we would want to know about the first derivative, and that would tell us something about the graph of f. And so we would take a value that's in the interval between negative infinity and 0, maybe like a value of -2, just as an example, and we would put that value into the first derivative. And in this case, that would be 4 times -2 cubed, which would be -32. And the important part is that the first derivative is negative, and that tells us that the function is decreasing. Now, in the interval from 0 to infinity, we need to pick a value, so +2 would work, and so then we put that into the first derivative again, and this is the first derivative test, of course, and so we would end up with 4 times 2 cubed, which ends up being +32. And so the important part is that the first derivative is positive, and so that says we're increasing. And we had a change in sign of the first derivative. That's the issue there. We have a change in sign. And so that change in sign, or knowing that we're going from decreasing to increasing, would tell us that we have a relative minimum. A relative minimum because we went from decreasing to increasing. And so we could have told that without looking at the graph that we have up above.
Let me remind you of why we just did this. Remember, originally we were trying to use the second derivative test to decide whether this had a relative maximum or a minimum. But when we put the first derivative critical number of 0 into the second derivative, we got a result of 0. And that's the place where, that's the situation where the second derivative test is of no use to us. It fails. And so we have to have another way to find out whether we have a relative maximum or a minimum, and that's why we had to revert to the first derivative test to make that decision. Now, what else is important here is that if we were looking for inflection points, so this is a separate issue altogether. The second derivative is also a way, not the second derivative test, but the second derivative is also a tool to find out where we change concavity or have inflection points. And so we go about finding inflection points by finding the critical numbers of the second derivative. And that's what we've done right here. And we found out that 0 is also a critical number of the second derivative. So at x equals 0, we might have an inflection point. And so we would have to go through a test to decide whether we had an inflection point. But you can see here the result of that test would be that we wouldn't have an inflection point because this is always concave up. It's concave up on the left side of 0, and it's concave up on the right side of 0. And so the point of this, the issue was that just because we have a place where the second derivative is 0, which is a candidate for an inflection point, doesn't mean that we will have an inflection point. So you always need to test for inflection points. This is separate from what we were doing, and that was the second derivative test. Well, this ends the issue with second derivative test. Go have fun using it.